Right, good. I don't think anybody's been kicked out, so welcome everybody. Okay, now I'm going to go over species and solution first of all, and then I want to go on to titrations, and with titrations I want to look at buffers as well, but we'll do it there, even though buffers is also dealt with in 306.2. Now, remember what I said with species and solution. These are all, by species I mean all the molecules, all the ions, any sort of type of particle you would find in a solution. So for instance, if I had a solution of hydrochloric acid, what species would I have in that solution? Obviously I'm going to have water, so we'll accept water, but what else would I have? I'd have the hydronium ions, correct, Layla? Okay, I'd have the chloride ions, okay, and then hydronium ions again. So Laura, you're saying they're from two sources, which is quite correct, and the hydroxide ions. Good. So I can see actually you actually know all your species in solution. Now, why don't you have the HCl molecules? Because I said I've got a solution of hydrochloric acid. Why don't I have HCl molecules in there? Because it's a strong acid and it completely dissociates. Good. So if I'm going to quickly go back to my different thing, I'm just going to quickly go. I'm pretty sure it's this one. I hope it is. No, it isn't. Sorry. I hope it's this one. Right. Okay. This is what you need to know off by heart for the exams. It is given in the assessment specifications or in the exam specifications. You have to know that the strong acids are HCl, HBr, nitric acid, and sulfuric acid. So those you won't be told are strong, you're expected to know that they are strong. Similarly for strong bases, they won't tell you that KOH or NaOH are strong, they expect you to know it. And then as far as the weak substances go, they expect you to know that HF, ethanoic acid, and the ammonium ion are weak acids, and for weak bases, the ammonia molecule, the methylamine or aminomethane, and the ethanoate ion are weak bases. So that is expected that you know that. Any other substance, they will tell you is either strong or weak, so you at least are given that backup information. Or they would remember, said if you get given a Ka or a Kb, is it strong or is it weak? You tell me. So if you get given a Ka or a Kb, it's weak. Okay. All right, so those, as I say, you have to know. If you need flashcards, for me, I also have found it very helpful writing things out. So if I wrote out strong acid, HCl, HBr, nitric acid, sulfuric acid, I'm a sort of visual learner, but kinetic as well, and that really helps me learn. You can do the same if it works for you. If you oral, have somebody recite it to you, or have a tape recorder going while you're sleeping, or video yourself. Now that tape recorders are very old-fashioned now. Okay, I'm going to go back to my other document. Oops, sorry, I clicked the wrong thing. Yes, I don't think any of you ever used a tape recorder. Have any of you used a tape recorder? Okay, you're still right. Okay, but now it's basically pretty much you can take a selfie, record yourself with your cell phone and everything years ago. Okay, so to try and work out what species are in solution, always ask yourself what it is. So by what it is it an acid or base or a salt? And if it's an acid or base, is it a strong acid or strong base, or weak acid and weak base? If it's a salt, so those are the four options we had here. So if it's an acid, is it a strong acid or a weak acid? If you've worked out it's a base, because then is it a strong base or a weak base? And then for the salt, you've got to work out, is it from a strong acid, strong base? Remember, a salt is always cation from what? The acid or the base? Because we get the cation from one part and the anion of the salt from another part. So the cation comes from what? The acid or the base? The base, correct. Okay, and the anion of the salt comes from the acid. So as I said, from sodium chloride, that salt, the sodium is a cation, it comes from sodium hydroxide, just add an OH or an oxide to it, and the anion, the chloride, comes from the acid, and the easiest way is to add H's to it. So if you had, for instance, potassium sulfate, what sort of salt is potassium sulfate? By that I mean, is it from a strong acid, strong acid, weak base, or weak acid, strong base? So think of potassium sulfate. It comes from the strong base, potassium hydroxide. The sulfate comes from, so now you've got to think of what acid involves sulfate. Okay, David, you've got there a weak acid. So just think of a sulfate. If you added H's to the sulfate, you'd have either HSO4 minus or H2SO4. Now, H2SO4 is, sorry, I can't, I could have it, write it down here. For us, remember what our strong acids were? They were HCl, HBr, HNO3, and H2SO4. And the weak ones we had to learn was the ethanoic acid. Sorry, I know this is a little bit slow. I can't really write very well with my mouse. We had the ammonium ion, and we also had HF that you had to know. Okay? Right, so it's strong. Yeah. HSO4 minus sort of sits in between. It's not 100% dissociates, but it's got a Ka of something times 10 to the minus 2. So a lot of it dissociates. It just simply doesn't dissociate completely. So it's sort of one of those, it's not really weak, but it doesn't come under the really strong category either. But you would never, at this level, deal with HSO4 minus. You just simply say sulfuric acid is a strong acid. Okay, if I asked you for ammonium nitrate, what sort of salt is ammonium nitrate? Is it from a strong acid, strong base, weak acid, strong base, or strong base, weak acid? So some of you are typing. So ammonium nitrate, so you've got to work out what sort of acid, so what sort of base does ammonium come from? Okay, and the acid, remember, is the anion, so nitrate. What sort of acid does nitrate come from? Laura, correct, a weak base, strong acid, because ammonium comes from ammonia, which is a weak base. Nitrate, if you added some H pluses to it, then it would be nitric acid, which is a strong acid. Okay, correct. Let's do one more. If I had, for instance, I'm trying to do one that's not given me. Let's make a potassium fluoride. What sort of salt would potassium fluoride be? So potassium, you've got to think of what base can I make from potassium. Fluoride, what acid can I make from fluoride? Okay, that'll be a strong base because potassium hydroxide or potassium oxide is strong bases, and fluoride, it comes from the weak acid HF. Okay, so that's when you get given a substance or given a solution, you've got to say, what is it? Is it an acid, a base, or a salt? And then you've got to say, is it strong, is it weak, or in the case of a salt, does it come from a strong acid, strong base, weak acid, strong base, or strong base, weak acid? So let's divide. I've given you some examples in here, but let's try and, well, actually I might as well work on here. So let's go through. If it's a strong acid, it's quite simple really. It breaks down completely to the hydronium ions and the anion. So as far as from the acid goes, that's all you've got. You've got no molecules in there. But at the same time, we've got to remember, and this came up earlier, water always has a very small amount of dissociation. So even if you've got a strong acid solution, you are always going to have some hydroxide present. Where does that hydroxide come from? So some of you are typing. The dissociation of water. So as an example of what I've got here, and I'll just change my color to, let's make it a sort of reddish thing. We're dealing with acids. If I've got a 1:1 ratio, so in other words, nitric acid is 1 hydronium ion to 1 nitrate, or hydrochloric acid is 1 hydronium ion to 1 chloride, I will have equal amounts of cation to anion. And as I say, always support your explanations with equations. So you could write, so if we had nitric acid, you could write HNO3 plus water forms the hydronium ion and the nitrate ion. Okay? Please check your charges as well and make sure you've got that there. That looks like such a bad squiggle. I hope you can see that as a positive sign. So you've got 1 nitrate to 1 hydronium ion, so it's a 1:1 ratio. If I had, though, HNO3, sorry, sulfuric acid, what sort of ratio would I have? Okay, 2:1, correct. So don't think you're always going to have a 1:1 ratio of hydronium ions to the anions. You have to look and see what is my ratio. And you can sort of, as I said, HSO4 minus is not quite strong, but you can sort of assume it. Okay, now your hydronium ions, David, correct, is you've also got hydronium ions coming from the water, but again, that's sort of very small amount, 10 to the minus 7 or less, or round about there. It's not very much. So we can always consider them to be approximately the same. If you want to insist, you can use a sort of squiggly equal sign. A squiggly equal sign means approximately equal. So you can use that if you don't want to use an equal sign. I would not use, if I just change to another color to make it cleaner, I would not say H3O plus, this is now say for nitric acid, knowing that nitric acid, hydronium ions come from 2 sources, so there is slightly more hydronium ions to nitrate. But I would not actually say that unless you explained it in words. Say you had that and then the nitrate is bigger than the amount of OH minus, because it looks as though that's sort of fairly straightforward. Lots of hydronium, not so much nitrate, and very little hydroxide, and that's not true. So either, instead of this, use the squiggly arrows or even the equal sign, and then perhaps mention it in your explanation if you've got space for explanation. Okay, so is it quite clear, in a strong acid, you've only got 3 species in solution, ignoring water, of course. Can you all see that? So it's the hydronium ion, the anion of the acid, plus a tiny bit of hydroxide from the water dissociation. Okay, let's look at the next one, which is the weak acid. The weak acid is something similar, except it doesn't dissociate completely. So if I had, for instance, HF, do I have any HF molecules in solution? Yes, because it does not dissociate completely. So if you were trying to write the equation for this, you would say HF, and I would now use an equilibrium arrow to try and show it doesn't lie completely to the right, and then I'd have the hydronium ions and the fluoride ions, because you should all recognize, hopefully, that HF is a weak acid. So what I'm going to have present in solution is I'm going to have HF in solution, I'm going to have hydronium ions in solution, and I'm going to have fluoride ions in solution. And then I'm always going to have, remember, the hydronium and the hydroxide from the water dissociation. What will be the most present? Will it be the hydronium ions, the fluoride ions, the HF, or the hydroxide? The HF, correct. And that's because it's a weak acid, and the weak acids you deal with only about between 1 and 5% actually dissociate. You don't use things like HSO4 minus, which dissociates a lot more. HF really hardly dissociates. So for every 100 HF molecules, perhaps 1 to 3 will dissociate. Okay, so HF is in the greatest amount, those molecules. What can you tell me about the hydronium and fluoride? They will be in equal amounts? Approximately equal amounts? And either of those is right, so you would say that they were equal, or if you wanted to be very specific, you could say there's a tiny little bit more hydronium ions from the dissociation of water. And then what's going to be in the least amount? The OH minus. Don't forget the OH minus, and again, always explain where it comes from. So don't just sort of make the list and say OH minus is the least amount without sort of saying where it comes from and why. So you can say it's the least amount because it's dissociation of water, and the equilibrium constant for the dissociation of water is very small. 10 to the minus 14 is tiny. Okay, let's go on to the strong base. So for a strong base, think of strong acid. How many species would we expect to have in solution? 1, 2, or 3? Great, Layla, you've already got the answer. 3. And that's exactly like the strong acid. We do not expect to have any of the base, well, not that sodium hydroxide is a molecule, but we do not expect to have any of sodium hydroxide as molecules. It's ionic anyway. So you wouldn't have Na, OH, but you would have the OH minus from the NaOH, and you would have the cation from the OH, so the sodium ions, and those would be in equal amounts, because again you would support your equation you support everything by writing an equation. So you're going to have a 1:1 ratio of sodium and hydroxide, so it is a sorry, Laura, I got sidetracked by your question and then I forgot what I was talking about. So you've got 1:1 ratio of sodium hydroxide, and therefore it's in equal amounts, or approximately equal. Okay, Laura, you've got I read in an old assessment schedule that if the student said that OH minus came from the dissociation of water, they could not score more than merit for that question. I'm wondering if they wanted also an equation to support their answer. That may be it. If they just made the statement. I will say when they write exam, I mean when you sit an exam and then they assess it, sometimes the markers can be very very picky on things because that's the way they've decided will be the easiest way to assess and make it standard across, all the different markers. So they may have come to that agreement for that. They may have wanted perhaps something a little bit extra like the KW of water, that it's very small, so there's only very small amounts. I'm just wondering if there was anything else put there for excellence. So, okay, while Laura's typing, yeah, okay, right. So we've got equal amounts of hydroxide to the sodium ions, and then we've got, as I say, the hydronium ions. And as I say, that comes from the dissociation of water, and always support your statements with equations. And you could even, as I say, from what Laura's pointing out, Kw is very small, so you'd only have a very small amount of hydronium ions. You'd actually have less than 10 to the minus 7, because remember your pH is going to be for a sodium hydroxide solution. It could be anything up to 14, so it'll be a very small amount of hydronium ions. Weak base. How many species do you expect to have present in a weak base? So we said a strong base and a strong acid were 3 species. Right, weak acid, weak base, you'd expect to have 4 species. And that's because you've got the undissociated molecules. So just like we had undissociated HF, we've got the undissociated ammonia in this example. But your ammonia molecule has reacted with water to give equal amounts of ammonium and hydroxide. So make sure you support your statement with equations. And then you've got that hydronium ions from the water dissociation. And just as they make it, always back it up with the equation. Right, so those are fairly straightforward. Just think of if it's strong acid or base, it's 3 atoms. If it's weak, it's 4 atoms in solution. And this is, also the extra one is always water itself. Water is always in the greatest amount. It's about 55 moles per litre concentration. Now, if you've got a strong acid, strong base, then you've got a salt from strong acid, strong base. Then the only trick is if you've got a ratio that's not 1:1. So like calcium chloride, or what else would you have? You could have sodium sulfate. So we'll assume that all of sulfate is strong at this level. Okay, so when you don't have a 1:1 ratio, then you don't form equal amounts of cation and anion. So I think that's fairly straightforward, but as I say, make sure you don't rote learn, if I've got a strong acid, strong base, I'm going to have equal amounts of cation or anion. Does that make sense? You've got to check the ratio. Okay. Is anybody not clear on that? And please feel free to say something, because somebody else might be too shy to say something. Okay, right, so if, for instance, in the case of calcium chloride or perhaps sodium sulfate, then the one that is got the most number of ions is obviously present in the biggest concentration. Notice, by the way, we use the square brackets. What do square brackets represent? The concentration. So it's concentration of the chloride ions. Okay, so if we had for sodium sulfate, we'd have what? More sodium ions or more sulfate ions? More sodium ions, correct. Okay. Right, and then, so if I have a strong acid, strong base, what is my pH like? So if I react a strong acid, strong base, this is where the titrations will come in very useful. What is my pH of? Okay, Layla, good try, but it's actually 7. So if I've got strong acid reacting with a strong base, I'm going to get a neutral, and by neutral I really mean neutral, I mean pH 7 salt. So for instance, sodium chloride will have a pH of 7, sodium sulfate will pretty much have a pH of 7, calcium chloride pH of 7. And so what can you tell me about my hydronium ions and my hydroxide ions? They're going to be equal. So for a strong acid, strong base salt, you're going to have the cation and anion of the salt, and whether they're equal or not depends on the ratio. And then you're always going to have the hydronium and the hydroxide that are equal amounts. And of course, these are going to be a lot less than the cation or anion, because you're only going to have 0.0000, think of 6 zeros and a 1, moles per liter of the hydronium ions and hydroxide, compared to, say, if I had a 1 mole per liter of the salt solution, that'll be 100 and, well, more than 1,000,000 times more concentrated. Okay, now these last two are pretty much the most complicated you could get. So if you can do these without a problem, there should be nothing any harder. This is when you have a weak acid strong base. So examples would be sodium ethanoate, potassium fluoride, or sodium fluoride, or what else can I think of? I know ammonium ion is seen as a weak acid, but of course that's a cation, so I can't make a salt out of that cation. If they give you any other one, like for instance, say even thinking cocaine's actually an acid, but I mean, I have sometimes seen them when they use weird things like that, but then they will have to tell you that it is a weak acid. Okay, they will have to say, actually another one that they use is benzoic acid. So if they have, for instance, sodium benzoate, that has come up in the past because sodium benzoate is used in food as preservatives and all that sort of thing. But you aren't expected to know that benzoate is a weak acid. They would have to tell you it's a weak acid, or they'd have to give you the Ka so that you can recognize it's a weak acid. Okay, so if I have a salt from a weak acid strong base, or the next one down, strong acid weak base, I have two sets of equations. My first set of equation is that my salt dissociates completely. So all my potassium fluoride forms potassium ions, and all my potassium fluoride forms fluoride ions. Okay, that's from what I think Andrew was asking earlier. Do I need to know my solubility? Well, if you knew that all group 1 salts are soluble, then you'd know that potassium fluoride is soluble. My next equation would be to have a look at the ions I've formed and work out which one is going to react with water. So the easiest way is to work out which one comes from a weak acid or weak base. Is it the potassium or is it the fluoride? The fluoride, because potassium comes from potassium hydroxide. It is a strong base. So remember we had here, so if I had here KOH, these are now the strong bases, and sodium hydroxide. And then we had the weak ones, which was methylamine, ammonia, and the ethanoate. And as I say, anything else they have to tell you. Hope you can read that. Okay, so going back to this one, you've got the fluoride. So the fluoride is going to react with water to form the HF, plus OH minus. So please make sure you support your statements with equations. Check that your equations are balanced. I've often seen somebody will write F minus plus H2O and then they'll gaily write HF plus H3O plus. Is my equation balanced if I write that? So F minus plus H2O forms HF plus H3O plus. Is my equation balanced? No. The quickest way to look before you start counting the atoms is do a charge balance. So for the first option here, okay, what is my total charge on the left-hand side of the equation? So if I count the negative charge, a charge on the fluoride and the neutral charge on the water, what's my total charge? -1. If I look on the right-hand side, what is my total charge? So what is the charge on HF? What is the charge on OH minus? So the total will be -1. Okay. If I look at my second equation that I had, so I had my F minus reacting with H2O, what is the total charge now on the right-hand side? So it's neutral on HF, positive on H3O plus. I have a total charge of +1. So okay, Siska, I know you've said naught, and I think you're looking at the left and the right, but what you've got to do is compare the left-hand side with the right-hand side. So you've got -1 on the left-hand side, +1 on the right-hand side. It's not balanced. You have made a mistake. Okay, so always use those simple checks to make sure you haven't made a mistake. Okay, so don't, it's easy when you're writing equations, you're under pressure to write the wrong thing. I've done it, but just do that double check with first the balance of the charges, but then also do an atom balance as well, because sometimes you can just be in a rush and even get your charges wrong. And then you make 2 errors and the errors seem to sort of cancel out. Okay, now let's look at the relative values. What am I going to have in the most amount? Kf, K plus, F minus, H2, well, I can ignore H2O, HF, OH minus. And then, of course, always the hydronium ion. What will I have in the most amount? The K plus, correct? And the K plus, because so little of this hydrolyzes, we can say that those two are in equal amounts. So, I mean, please don't do this in the exam by ruining your nice equation by putting in the concentration things around there, but you get what I mean there, that you can say that those are equal because so little F minus actually hydrolyzes. Okay, so those are in equal amounts. What comes next then? Okay, the Kf, Layla, is no, because this is where the solubility rules helps. All potassium salts, because it's in group 1, are soluble, so you will not have any Kf in solution. It'll always exist as K plus or F minus. Okay, and never as Kf. And that's why I say if you know your solubility rules, it really sort of just gives you that extra confidence. Okay, so you've got, for the others, okay, the hydronium ions will be in the least amount because we've got a weak acid strong base, which means because I've got a stronger base, it's going to be a basic solution. So I'm never going to have more hydronium ions than hydroxide if it's going to be a basic solution. But it's a good point you raised, Laura. So what I'm going to have next is equal amounts of HF and OH minus. Okay? My K all dissociated to form K plus and F minus. Tiny little bit of my F minus reacted with water to form equal amounts of HF and OH minus. And then I always have, oh, can't you see the bottom of my screen? Thank you. Is that better? Yep. And then, of course, I'm always going to have a tiny amount of the hydronium ions because of the dissociation of water, and you can say remember your equation is always 2H2O is in equilibrium with the H3O plus and the OH minus ions. But of course this is very tiny because this equilibrium is 10 to the minus 14, the constant. So I'm going to have even less of the hydronium ions because I've got a strong base. So that's always last. Always think of what is my pH of the solution expected to be, and if it's going to be more than 7, the hydronium ions must be last. If it's going to be less than 7, then the hydroxide ions must be the lowest. And if it's equal to 7, then I must have equal amounts of hydronium and hydroxide. So just as I say, do that. Is my answer sensible? Check. So the final thing now we're going to do is from strong acid, weak base. It's exactly the same sort of thing, except now we've got a strong acid, like the anion comes from either HCl or HBr. So I've either got a chloride, a bromide, a nitrate, or a sulfate. And my base must be either ammonia, so in other words NH4Cl for instance, or it could be the methylammonium ion, so I could have for instance CH3 NH3 so 4. I hope you can recognize that, because you should know that the methylammonium ion, it's a 3 there and not a 2, because remember this has got a positive charge on it. You don't write the positive charge if you're writing it as a normal salt, just like you don't write Na plus Cl minus, you just simply write NaCl. When it's in a solid, the same thing, you don't write the charge in, but that's where that single charge comes in. So that's, for instance, an example of a weak base strong acid salt, or I could have methylammonium bromide, or I could have had methylammonium nitrate, any of those combinations. So do I need to go through this one, or do you think you can work out the strong acid weak base? Right, okay, some of you are typing. While you're typing, I'm going to go to the next screen. And what I'm going to do, I'm not going to actually list the species in solution for all of them. I just want to check, because you need to also do the properties as well. So if I've got a solution of methanoic acid, now I would have to tell you that that is a weak acid, because it's not one on the given list. So I'm going to tell you it's a weak acid. Can you tell me what is its pH going to be for, say, a 0.1 mole per liter solution? Is it going to be a pH of 1, a pH of around about 2 or 3 or 4, or a pH of 7, a pH of 10, pH of 14? 2 or 3 or 4. It's going to be one of those weak acids, depends on exactly where the equilibrium constant is. Okay, so you should be able to work out its pH, approximate pH, just by looking at it, without even giving a Ka value. What can you tell me about its conductivity? Would the solution be a very good conductor? A poor one, it will be a weak conductor. And why is that? Because it forms very few ions in solution. Only about 2 or 3 might dissociate out of every 100, so it doesn't have very many ions to conduct the charge. What can you tell me about, well, I've pretty much done that, conductivity and the pH. When you explain this, by the way, when you talk about pH, please refer to the amount of hydronium ions. Okay? Be specific. Say it doesn't have very many hydronium ions in solution. When you're referring to conductivity, what do I need to refer to? So some of you are typing any of the ions, charged particles, correct. So say these little dissociations, so there are few ions. So if you like, the concentration of the ions is small. Okay, so there are few ions, because remember, both the hydronium ions and the methanoate ion could conduct electricity. It's just they're in such small supply that there's not enough of them to do a proper job. Okay, so just make sure you show that you know that difference. So let's look at, do you want to do any of these in terms of the amounts? So is there anyone here that you can look at and you go, ooh, I wouldn't know how to answer that one? So that's about as much as they are. So you think you could do all of them? Okay, I'm going to do one because I included this one because it's really a bit of a trick question. What is that? Okay, David, by amounts of what? I meant relative amounts of species in solution, because you guarantee to get a question on that. Okay, so what is that number 4 that I've highlighted? So strong acid, strong base, weak acid, weak base, salt of strong and strong, salt of strong acid, weak base, salt of weak base, strong acid. It's a weak acid. Correct, Layla. As I say, it's not given on your list, so they would have implied it somewhere along the line by giving a Ka. But I'm just pointing this out because it's so easy to read that as HNO3, nitric acid, instead of nitrous acid, which is what that is. Okay, so that was not a typo. That was actually the nitrous acid, which is a weaker acid. Right, okay, so I'm going to leave that there. We've got now about 15 minutes, and I do want to go onto the titration curves. The titration, I'm going to just stop sharing, and I'm going to share my screen now. And it'll eventually come up. Right, okay. Now in OTIL, you access all these different simulations, and we've just had our computers all updated, and I've